I assume we are live and we can check that on YouTube to make sure. Uh, Liv wants to do that. But welcome everyone, and I'm glad everybody could show up here in virtual land to see our speaker tonight and listen to his talk. So I appreciate all your time. And of course, I appreciate our speaker's time with us tonight here as well. So my name's Dr. Sean P. McBride. I'm in the Department of Mathematics and Physics here at Marshall University. So obviously the Society of Physics students here is tied to that academic unit. And I really want to first thank Sydney. So she's really helped organize a lot of the speaker series along with Liv as the president, sort of guiding everybody as well. So I appreciate the time you both have spent trying to organize the speaker series this semester. Fantastic job there. Like I said, our program here is the Department of Mathematics and Physics. Within the physics department here, or within the physics program, we have about 7 faculty members. 4 of us are active in research, and we have 3 teaching faculty at the assistant professor level as well that are full-time teaching faculty. We have over 20 faculty members in the mathematics program. So we are essentially a department that is a vibrant community of scholars that is passionate about exploring the fascinating intersection between mathematics and physics. We have several different programs, and we have undergraduate BS in mathematics, an undergraduate BS degree in physics, as well as an undergraduate BS degree in statistics. At the graduate level, we have a Master's of Arts in mathematics. We also have a Applied Sciences Master's program, and as well as a Physics Master of Science program. So Marshall University has been often described as just the right size university. We are not a large R1 university, but we are an R2 university designated within the last couple years. We have about 8,300 students, undergraduate students, and about 2,400 graduate students. We also have about 550 students that are in professional programs such as PharmD and MD and the like. Over 85% of our faculty have terminal degrees in their field. We have a low teaching student-teacher ratio, so it's about 17-to-1. So average undergraduate class size is about 20 students, with graduate classes less than or around 10 students. If you have any questions about any programs at Marshall University or programs within the mathematics and physics department, feel free to shoot me an email, and if I don't know the answers, I will certainly get you in touch with somebody that does. So my email is mcbrides@marshall.edu, so MCBRIDES at marshall.edu, and I will be happy to assist you with any questions. And of course, if you have questions about tonight's talk from our speaker, I'm sure he will be more than happy to connect with you and answer any questions via email as well. And we will have questions available on YouTube. So please type your questions there, and Sydney will read those to our speakers so that he can address those. So I think without taking up too much time, I will pass this back over to Sydney, and she can better introduce the club as well as our speakers. So Sydney.
Thank you, Dr. McBride. I want to thank everyone real quick who's going to be joining us tonight. Society of Physics Students at Marshall University is a nationally recognized chapter. Our group is made up of students from all different major discipline backgrounds, and you do not need to be a physics major to join. We meet biweekly through the fall and spring semesters and do public outreach, generally with surrounding area schools. Another portion of what our club does is the Faces of STEM speaker series. This speaker series originally started as the Faces of Physics speaker series, but has evolved to include diversity in speaker fields to represent our own diversity interests within the SPS group. The series is open to all, and we welcome the opportunity to highlight the work of researchers from underrepresented groups to promote inclusion and inspire the next generation of scientists to find their place in exciting STEM fields. Tonight we have joining us from Ithaca College, Dr. Jerome Fung with his talk, Manipulating Colloidal Particles with Light, Simulations and Experiments. Dr. Fung is currently an associate professor of physics at Ithaca College, where he teaches courses across the curriculum and mentors undergraduates in optics and soft condensed matter research. Before coming to Ithaca College, Jerome was lecturer of physics at Wellesley College. Prior to that, he performed postdoctoral research on colloidal membranes formed in the filamentous bacteriophages at Brandeis University. Jerome earned his PhD in physics at Harvard University, studying holographic microscopy and colloidal suspensions. Jerome completed his undergraduate studies at Swarthmore College, where his first exposure to research was in experimental plasma physics. Thanks again to all of you for coming, and a huge thanks to Dr. Fung for taking time to talk about his work amidst his busy schedule. I will now turn it over to our speakers. So without further ado, Dr. Jerome Fung.
Okay, thank you very much, Sydney, for the introduction, and thank you to Liv for the invitation to join you all tonight. So let's see, let's get the screen share going over here. All right, can everybody see? Okay, so all right, so here we go. So thank you again. So I am Jerome Fung from Ithaca College in a little chilly right now, Ithaca, New York, up in the Finger Lakes. We're maybe we're maybe about 2 hours from Niagara Falls, if you know the area at all. So what I'm going to be talking to you about tonight is broadly speaking, exerting forces with light. Now, this is a fun thing if you like science fiction, and maybe there are some Star Wars or Star Trek fans out there, and you've seen things like tractor beams, in movies. But this isn't just science fiction; it's actually reality, using something that we call optical tweezers. And the idea is that you can have particles, so things that are like a micrometer-sized bead, or even things like bacteria that get drawn to the center of a focused laser beam. Near the center of the beam, there is a spring-like force that tends to hold particles stably in equilibrium. And this is great because you can both use optical tweezers as a means to exert forces on particles of interest, as well as to measure forces that are exerted on a particle by something else. So you've probably all done introductory mechanics labs where you use a spring scale to measure forces. Optical tweezers work the same way, right? If you know how far your spring is stretched and you know the stiffness, you can infer something about the force that's pulling on the end of it. Same thing over here. I would be remiss if I didn't mention that optical tweezers led to the 2018 Nobel Prize in Physics for Arthur Ashkin. So why should I care about this? So there's all manner of really interesting things you can do with optical tweezers. The ability to grab onto things like small particles or bacteria means that you can do things like assemble interesting structures in situ. So I'm showing you a movie here that's an animation reconstructed from experimental data, where some of my coworkers in grad school and I were watching how a bunch of small spheres that were weakly interacting arranged and rearranged themselves in a cluster. And this kind of experiment was only possible because we were able to grab onto some particles and bring them close enough to interact with each other using optical tweezers. But that's not the only sort of thing you can do. So there's a large piece of optical tweezers research, which is involved in measuring forces exerted by biological molecules. So this is I grabbed a still from a pretty famous animation of, in this case, we have a motor protein, kinesin, walking along a microtubule in a cell, dragging some cargo behind it. And the cool thing is that you can study this process with optical tweezers, and you can literally use optical tweezers-based measurements to observe this molecule essentially stepping forward along the microtubule. So I'm going to focus here not on that kind of thing, but I'm going to be focusing on manipulating what we call colloidal particles. And so colloidal particles are a suspension of solid particles in a fluid. If you take a sample of this in a lab, it might look something like this, where you have you have a little. Let me make sure I have a pointer here. Okay, so let's see. Sorry, let me see if I can pull up a pointer here. Or can you see if I'm pointing on? Can you see my pointing on the screen or not?
I can, yeah.
Okay. Okay, yeah. So if you have a sample of colloidal particles, uh, it might just look like, milk. But if you zoom in on this under a microscope, what you'll see is a background fluid and some small solid particles. So maybe something like polystyrene beads, or maybe silica, which is basically glass. The particle size range usually runs from maybe in the tens of nanometers up to several micrometers. And so this is big enough that the physics is essentially classical. Quantum mechanics has basically no direct relevance for anything I'm going to talk to you about tonight, but it's still small enough that some interesting things happen, as I'll try to show you. So why colloidal particles? Right there's a good bit of practical relevance. So things like paint, right, is a colloidal suspension. Milk itself is a colloidal suspension. One of the things we'll talk about later on in this talk, Brownian motion, so the random motion of colloidal particles in that fluid. There's also a lot of work that's used colloidal particles as model atoms. It turns out that in some cases you can adjust the interactions between colloidal particles to be similar to those that you might expect in an atomic system, like a chunk of metal. But unlike the atoms in a chunk of metal, you can actually see and manipulate colloidal particles under a microscope. So here's what we'll talk about this evening. So Liv had asked me to talk a little bit about how I got into doing this sort of thing. So I'll tell you a little bit about my background as a scientist. We'll talk a little bit about how and why optical tweezers work. And then we'll talk about some of our work on simulating the behavior of colloidal particles in optical tweezers and some related types of beams. And then we'll also talk about some of the experimental work we're doing in my lab involving colloidal particles and optical tweezers. So just a little bit about me. So I grew up in New Jersey, and then went to Swarthmore College, which is a small liberal arts college about 20 minutes outside of Philadelphia for my undergraduate work. So there's a shot of the campus. So my first exposure to research at Swarthmore was in experimental plasma physics. So plasma is ionized gas. And so the sun, for instance, and frankly, all stars are made of plasma. And I was involved in a project where we were trying to look at and measure flows in a plasma. And it was a cool experiment where we were doing spectroscopy, and we were specifically trying to look at the Doppler shift in light emitted by ions in the plasma. So you might have talked about the Doppler shift for sound waves, like, if you have an ambulance driving by you, or for light, in a class on relativity. But essentially, by looking at whether these spectral lines were Doppler shifted, we could infer something about how the plasma was moving. So this was sort of my first sort of work on an experiment that was heavily optics related. And I think sort of in hindsight, that sort of ended up steering me towards what I do now. I also had the chance to spend a summer doing an REU, a research experiences for undergraduates at the University of Iowa, also on plasma physics, but on a different area, namely dusty plasmas. So dusty plasma is you have a plasma, and then you put in some solid particles that tend to charge up, and they can do interesting things, like they can form these two-dimensional crystal lattices. Now, if sort of the idea of putting solid particles in something sounds familiar, well, there is actually some analogy between colloid physics and dusty plasma physics. So again, maybe that's another place where I kind of started getting interested in that sort of thing. So after my undergrad, I went on to Harvard University for graduate school, and I chose to join a group focusing on soft condensed matter. So I found a couple of pictures of us. I think we're at a dinner celebrating somebody's graduation or something. Here's one of my coworkers on one of the microscopes we were working on. Some shots of us in the lab office. Looks like, again, celebrating somebody's thesis defense or something. And then here's me with my advisor, Dr. Vinny Manoharan. So just a little bit about what I've worked on in graduate school. I was working on a project that involved trying to track clusters of colloidal particles in 3 dimensions using a technique called digital holographic microscopy. So if anybody's ever, anybody ever does, photography, for instance, right? If you're, it's not always easy to do like action photography because things will move in and out of focus. That's true for colloidal particles under a microscope too. So we were working on a way to be able to localize particles in 3 dimensions by sort of changing how we do microscopy. The idea is that we would illuminate a sample with particles with a collimated laser beam, and some of that laser beam scatters off the particle. And then if you record downstream the interference pattern between the incident beam and what scatters from the particle, you get this sort of ring pattern that's called a hologram. And as long as you have a way to predict what the hologram should be for a given set of experimental conditions, you can then go and fit your model to the data you actually record, and then back out things like where your particle is in 3D. So here's something from my PhD work where we were tracking this cluster of 3 spheres. The bottom is an animation computed from the data over here. Here's our best fit model of that, and we can track this thing tumbling around 3-dimensionally. So after that, I went on to Brandeis for some postdoc work. Wanted to shift gears a little bit, and I worked on more colloidal physics, but in a pretty different domain. So I worked on a system of membranes. So it turns out, the things that made up the membrane were these rod-like viruses that are about a micrometer long. There's nothing particularly like biological about these, and it's not like we were using viruses as viruses per se. It's rather that nature is way better at making really uniform things than human chemists are. And so anyway, we were looking at the physics of these membranes where you assembled them from these rods and these membranes were sort of 1 rod thick. So more colloids, but also more optics, right? Because this was an experiment where I was trying to manipulate these things using optical tweezers. So maybe it's kind of become apparent sort of how I've developed some of the interests that I have, sort of drawing from the different things I've had the opportunity to work on over the years. But even as I've enjoyed doing research, I always knew that teaching physics was something I really loved doing and wanted to spend a lot of my time on. And that led me to pursue jobs focused on teaching. So my first faculty position was in a teaching role at Wellesley College, which is in Massachusetts. It's an all-women's college, about half an hour west of Boston. So that's me with one of my colleagues and some of our students. And then from there, I joined the faculty at Ithaca College in 2018. So here's me with some of actually my students this semester. Here's when shortly after I joined, when one of my first research students and I were trying to set up some stuff in the lab, and we were trying to connect some compressed air plumbing under this new optical table. So I would be remiss if I didn't give a shout out to the students who have contributed to the work I'm going to be talking about. So folks who have contributed to the simulations that I'll show you. So Yash, and why it really kicked off that project. Folks who have worked on the experimental side of this, we've got Jose and Charlie most recently. But earlier, right, Chris sort of built the first stages of the experiment. He was the guy under the table on the last slide. Oscar also made some really key contributions, and Emily worked on some of the chemistry aspects of this project. Okay, so let me now tell you a little bit about how and why optical tweezers work. Okay. So here's sort of an overview. Achieving just a single point optical trap is not actually all that difficult. Essentially, all you need is a laser. You probably want to expand the beam with a pair of lenses that form a telescope, but then all you need is a collimated laser beam and a really good microscope objective lens. And if any of you have ever tried to set something on fire by focusing sunlight with a magnifying glass, you'll know that if you shine light through a converging lens, the rays will converge to a point. Now it's not quite a point because of wave optics effects, but that's basically what optical tweezers are. You just have to take a laser beam and focus it down. And if you do this, you can get something like this. So this is a movie we got pretty early in my time at IC. And here's a movie where we've got a particle held in optical tweezers. The trap's on now. We turn the trap off. The particle can move around. We turn the trap back on, and it comes right back. Let it go again, and repeat that a couple of times. So some of our questions are, right, how and why does this work at all? And how can we predict the forces that optical tweezers exert on particles? So the way I like to explain this, especially to my students who are starting out, is to think about photons and to remember that light carries momentum. Many of you may be familiar with the idea that light has particle-like properties and that you can relate the momentum of a photon to its energy. So it's sort of like this. So if light has momentum, it can also transfer momentum. Some of you may have thought about a situation like this in intro mechanics, where, right, this person on a cart, throws balls that bounce off a wall. If you think about the balls and the cart and the person as a system, right, if in the final state, right, this ball is going off to the right, right, if the system initially had no momentum, right, the person in cart must have some momentum pointing to the left, right? And we can think of essentially, right, momentum has been transferred sort of within the system from this ball to the rest of the cart. You can think of light as doing essentially the same thing. And you might call that radiation pressure. And this actually has some cool real-world consequences. So if you look at things like comet tails, right, there you can actually see radiation pressure from the sun affecting the shape of those comet tails. Okay, so here's sort of the simplest argument for why you might get stable optical trapping. And we're going to assume that geometric optics is valid here, so we're going to be thinking about tracing rays. So here's the scenario. So we've got a laser beam that's drawn here in red. Let's assume that this beam is propagating upwards. And we also have a particle here that in blue, where the particle is slightly below the focus of the laser. And we're also going to assume that the particle has a higher refractive index than whatever is surrounding it. So the argument really hinges on following some rays in the beam as they interact with the particle. So let's look at these two rays, labeled 1 and 2 here. So again, thinking like we might in intro mechanics, we can think of the light rays in the particle as forming an isolated system, right? The direction of the momenta of the light rays is the direction of propagation. So if I take these two rays here, right, they have momentum vectors like this. And then, right, if I add them, right, the horizontal components cancel, I get an initial momentum for the light that points up. Now, let's imagine tracing the rays through the particle here. So if we focus on ray number 1, right, by Snell's law, the ray has to bend towards the normal, crossing into a higher index medium, travels straight through the particle and then bends away from the normal, going into the lower index surroundings on the way out. So the final directions of ray 1 is over here and of ray 2 over here. And if we apply the same argument, right, these two vectors now point out a little bit more. And that means that if I add them, right, the final momenta of those two light rays still points up, but is a little bit shorter. Well, where did that momentum go? We know that there was a change in momentum for the light that pointed downwards. Well, the only place this could have gone would have been to the particle, if my system is isolated. And this upward transfer of momentum to the particle manifests in an upwards net force on my particle. You can sort of extend this sort of argument to sort of this ray tracing argument to particles that are in different positions relative to the focus of a trapping beam. And the result ends up being the same, that the particle ends up being drawn to near the center of the beam. There's a problem with this. Even though this argument is sort of, it's intuitive, it turns out not to be quantitatively valid for micrometer-sized particles. And the reason for that is that typically we're looking at particles that are sized roughly at about a micrometer, so 10 to the minus 6 meters, or maybe something like 50 times smaller than the size of a human hair. In the experiments we do, we're usually considering light the wavelength around that, so around 1,000 nanometers. But as you might have learned, in optics, right, geometric optics is only valid when you're dealing with things that are much larger than the wavelength of light. So again, this is great for getting a qualitative sense of what's going on, but it isn't useful for making quantitative predictions. Okay. So some of the things that we want to be able to answer sort of through doing some computational work is, how can we predict forces and torques on wavelength-sized particles in optical tweezers? We'd also like to be able to predict the behavior of those particles. And more broadly, can we simulate the sorts of things we see in experiments? And maybe can we even simulate things that we can't yet easily do experiments on? Okay, so now let's talk a little bit about how, in my group, we computationally model the behavior of particles in optical tweezers. So the way to get around ray optics not being valid is to really think in terms of light as a wave. And it turns out to be useful to think about this as a scattering process. Here's how I like to think about it. As you may have learned in E&M, right? In general, electromagnetic fields carry momentum. So let's imagine we have a situation where we just have a beam. Again, let's say this beam is propagating upwards, and there's nothing here, so no particles here. Let's imagine sort of a large imaginary sphere that's surrounding the beam. So this thing that I drew in orange. Now, if we know that if there's nothing here, there aren't going to be any forces exerted on anything inside this imaginary surface. And so if we think of the fields from the light as carrying momentum, the result is that the momentum flux through this imaginary surface has to be 0. Now, if we add a particle in here, right, the particle is going to scatter some of the incident light. That means that the electromagnetic fields on this imaginary surface are going to change. And now, if with these changed fields there is a non-zero momentum flux on the particle, then there'll be a force on the particle. So essentially, we're able to predict optical forces and torques on particles if we can predict how that particle scatters an incident beam in the far field. And this is a hard problem, but fortunately, it's a doable one in many cases, and something that lots of people have been exploring for decades. Okay. So that's sort of a piece of it, but then there's more than just the forces, the optical forces going on. So it's easiest to see, when the trap turns off, right, which it will in a second, right, the particles just start moving around, right, sort of randomly moving. But if you watch carefully, even when the trap is on, there's a little bit of jiggling going on with even when the particle is held in the optical tweezers. So what's going on here, right? The particles are undergoing Brownian motion. Essentially, the way you want to think about this is that if you're at non-zero temperature, right, everything's moving. So all the molecules in the water here are moving, and they're randomly colliding with the larger colloidal particles in this experiment. And so the effect of those random kicks is that when the trap is off, right, you get this sort of quite visible motion of the particles. And when the trap is on, you still those kicks can't eject the particle from the optical tweezers, but they can cause that jiggling you see. So how do we simulate this in practice, right? So we're working with colloidal particles in a fluid where for really small things in a fluid like water, viscosity is really, really dominant. It'd be something like if you were to imagine like things the size of us trying to swim through really thick honey or molasses or something like that. So essentially in the in this sort of overdamped limit, right, inertia doesn't matter, right? Things only move as long as there's a force, acting on them. It's sort of like this is the world where sort of naive mechanics, all the things that we try to, we talk about Newton's, first law, in intro, right? This is the world where sort of folks, people's sort of naive ideas about Newtonian mechanics actually work because drag is so dominant. And so the idea is that we can basically simulate a trajectory for something, for a colloidal particle, just by thinking in discrete time steps and in calculating a displacement at each time step. So this generalized displacement here, which involves both translation and also rotation, has a couple of contributions. There's a piece that's just random, that's that Brownian motion, and we just need to be able to draw random numbers in a particular way. There's also a displacement due to external forces and torques. These are the forces and torques from the optical tweezers, which I've already sort of suggested how we can calculate. And I'm not going to go into all the gory detail here, but essentially, each of these pieces, there are some well-established methods for calculating. And so if we put all of these things together, we can actually simulate pretty close to what we actually see. So here's that experiment video, and here's a corresponding sort of simulation video. The trap, where we can again turn the trap's on now in the simulation. We can at some point let the particle right. At some point we'll let the particle go, and right, it wanders around, and then in the simulation we'll probably turn the trap back on again, and the particle is once again held near the center of the box. I'll be showing you a couple of these sort of renderings where I'll just point out here we've got an imaginary box where the trapping beam is propagating upwards in the positive z direction. So hopefully I've convinced you that like in simulation we can reproduce the same sort of behavior we see in experiments. But that's not all we can do. So we can also imagine putting some particles that have more interesting shapes in our simulation. So here what I'm going to show you is a movie of a rigid cluster of two spheres that are rigidly stuck together. The spheres are optically uniform, but I painted some stripes on the spheres so that you can see what's going on. And in optical tweezers, you can see some interesting things start to happen. So you see that first of all, you've got some this cluster, which we call a dimer, spins about its long axis. So you can see sort of the stripes turning. But then the axis of the dimer also sort of wobbles around the center of the beam. And essentially, the spin, at least, we can attribute to the fact that what I didn't tell you is that this is the beam here has circular polarization. And it turns out that the beam carries some spin angular momentum. And that spin angular momentum can actually couple to the particle and give rise to the spinning that you see here. Okay. And you can also do this sort of thing for more complex shapes. So here's a 7-particle cluster, which sort of really has sort of no meaningful symmetry. Once again, we can sort of simulate this thing, and this one, it turns out, happens to have multiple stable trapping equilibria, which is not something you see for the for either single spheres or the or for more symmetric things like the dimer I was showing you before. More recently, we've been looking at beams that aren't just optical tweezers. So optical tweezers are what we might model as a Gaussian beam. And there's something called a Laguerre-Gaussian beam that is a generalization of that. So here's sort of the lowest order Laguerre-Gaussian mode, which is a Gaussian beam. Here's a slice of the intensity sort of running across the beam. So imagine the beam propagating like out of the page over here. Here's another cut. This time the beam is propagating upwards. And what you can see, right, is that for this Gaussian beam, there's the intensity is highest in the middle and then dies off. And you can also kind of see this where it's sort of focusing in, really intense over here, and then sort of diverging out like that. Importantly, the optical phase of the light is uniform in any sort of transverse plane, as you can see over here. Now, what's interesting is these generalizations of Gaussian beams, right, include things that we call donut beams or optical vortices. Now, right, instead of having an intensity maximum at the center, right, there's an intensity minimum here. And instead, what you see is sort of this donut-shaped pattern of intensity around the center of the beam. And this time, right, the phase does vary going around in a transverse plane. And beams like this actually carry orbital angular momentum. And so you might ask, how do particles or clusters of spheres behave in these optical vortex beams? Well, if you have non-absorbing spheres, they'll just stably orbit in that donut. And so this is exactly what we're seeing here. So you can see this blue particle just going around and around the z-axis, which is the direction of propagation. And so this is the optical forces alone are stably holding the particle, and again, this is reproducing some stuff people have seen in experiments before. What's nice about simulations is that it's relatively straightforward to systematically vary parameters of the experiment. So we can, for instance, see that the radius of the orbit doesn't depend on the power of the trapping beam, but that there are some differences depending on whether your beam is left or right circularly polarized. And that there's also some effects that as you change the mode, you basically change the size and structure of the donut, and you therefore see some changes in the orbit radius as you change the mode. So everything we're seeing here is consistent with with theory in terms of sort of order of magnitude type calculations and experimental work. What we're doing now in my group is we're doing things like looking at clusters like those dimers in these optical vortex beams. I'm not going to go into too much of that stuff so that we have some time to talk about experiments. But if anybody is interested, please let me know. So in this sort of last section of the talk, I'd like to tell you a little bit about the experimental work we're doing with optical tweezers. So our broad goal is to better understand interactions between a particular type of colloidal particle. So instead of being sort of uniform spheres like the beads I showed you earlier, the particles we're interested in have a core shell structure. So they're really, really squishy. On the outside, there's this sort of polymer brush, this sort of hairy brush here that surrounds a much harder core of polystyrene. And this outer polymer brush layer turns out to be temperature sensitive. If you heat it up a little bit about room temperature, the shell will collapse. And this is nice because now you can essentially change how much of your sample is sort of occupied by particle. And that turns out to be the key thermodynamic parameter if you're interested in the phase behavior of colloidal particles. What we're particularly interested in is potentially using these particles as a way to understand the glass transition. So glass is really common, but not very well understood in the sense that it has liquid-like structure, but solid-like mechanical properties. And there's been a lot of work using colloidal particles to study glasses, but one of the challenges is that colloidal particles with sort of what we call hard sphere interactions, so things that act like billiard balls, may not actually model atoms all that well. And there's reason to think that really squishy particles like these might be a good model system for better replicating what we see with things like window glass. The only trouble is that the interaction between particles like this is not very well characterized. And that's what we're trying to do long term. We're not there yet, but that's our goal for going forward. So how do you measure colloidal interactions with optical tweezers? Again, if you've taken intro mechanics, you've probably done things where, like, if you watch a projectile fall, you can learn something about little g, right, from looking at the trajectory. So you can do a similar thing for microscopic particles, only you've got to deal with the Brownian motion. So if you have two particles that are interacting with each other, there'll be sort of random Brownian motion, but it'll be biased because of the interaction between the particles. And the idea is that if you can sort of set two particles near each other and then let them go and watch them interact, and then grab them again and then watch them interact, let them go, watch them interact again, and sort of do that over and over, if you look for long enough, you can build up enough statistics and essentially uncover any bias in the Brownian motion. And that's what we're aiming to do. Now, in order to do this, you need to be able to grab onto two particles at once, and those particles can't be in the same location. So you need multiple optical traps. You can actually do this, though, by you can make multiple traps at once using something called holographic optical tweezers. And the key to holographic optical tweezers is something called a spatial light modulator, or SLM. You've probably all seen these diffraction gratings where you have a piece of plastic with so many lines per per millimeter. But if once you get these from the factory, right, you can't change anything about the pattern. What's cool about a spatial light modulator is that this is essentially a programmable diffraction grating where I can display on this SLM a pattern, but then I can change it basically at video frame rates. So this is what this thing looks like in the lab. There's a liquid crystal element here where pixel by pixel you can adjust the phase shift that light reflecting off this element gets. And so you can do things like I can display a diffraction pattern that looks like maybe similar to lines. This sort of diffraction pattern gives you a lateral shift of your beam. You can display these sort of bullseye patterns to sort of shift the axial position of your beam. But you can do sort of both of those things at once. So here's the sort of pattern you would display to generate a pair of traps, one shifted laterally and the other shifted axially. So here's what this looks like in the lab. So we've got a now much more populated optical table. We've got our laser over here. Beam gets expanded and bounces around off my spatial light modulator and then goes into this homemade microscope here. And here's two of my students, Jose and Fiona, working on the microscope. There's no eyepiece because, right, with lasers, you can't look into this thing. So everything we do is, we look with cameras. So, so here's a little bit of data. So to show you that hopefully that we can actually trap two particles simultaneously. You see a little bit of jiggling there. So, but the particles are held stably, and you've got two particles that are separated by, maybe something like 15 microns or so. But the cool thing about holographic optical tweezers is that, right, the particles don't have to be in the same plane. So in this next video, what you're seeing here is two particles. They're both held stably. But right, notice how this one looks a lot more out of focus, right? Because it looks a lot fuzzier and like has this sort of like aura that extends out further. Well, that's because this is in a different plane, and it turns out the particles here are separated by 4 micrometers along the optical axis. So this one's in focus and that one's not. And once again, we can stably trap two particles, basically wherever we want. Okay. So again, this is work that's still ongoing, and we've got more things to do. But hopefully, I've convinced you in this talk that optical tweezers are useful and really interesting, and that we're able to simulate the behavior of sphere clusters in focus beams, and that there can be some interesting couplings between light and particle motion. And right now, we're continuing to work to push on this optical tweezers experiment to measure the interactions between these squishy colloidal particles. So I'd like to thank sort of all the agencies without which this work would not be possible. We've run the simulations on a cluster at San Diego. There's funding support from the American Chemical Society, and also we've used resources at the Cornell nano facility on the other side of town. So thank you very much. If anybody has questions, I'd be happy to take them. And you can also contact me by email, jfung@Ithaca, if you'd like to continue the conversation.
All right, thank you very much. So I think Sydney here will be looking at the chat, and there'll be a little bit of a delay here. So maybe I'll ask a question here while we're waiting for maybe some viewers to ask a question.
Sure.
What have been some applications that maybe has surprised you to see where optical tweezers have been used recently, maybe where you were like, wow, I didn't think that was possible?
Well, that's a good question. Well, I can tell you about one funny one that okay. There are the serious ones, and then there are the funny ones. There was a group at I think the University of Edinburgh, I think, or Glasgow, which had one of these multiple beam optical tweezer setups, and they actually got they got like 8 particles, and they got them to like. And they got the particles to do a Scottish Ceilidh dance and sort of set it to music. So that so that's silly. Another so one of the but fun. And another and there's some real science there in terms of like thinking about how you like calculate optimal patterns for doing that kind of thing. So it's not totally silly. Well, sort of one from my own experience when I was a postdoc doing these colloidal membrane experiments, you can basically use optical tweezers as essentially as a really expensive vacuum cleaner. And in particular, right, we in these experiments, right, we have these colloidal membranes, but what I didn't tell you is that we sort of hijack E. coli bacteria to not the kind that make people sick, but right, we harness bacteria to grow our viruses, and then Anytime you have a sample of the colloidal membranes, inevitably you get some bacteria in there, and those are really annoying when you're trying to do an experiment. So you can totally use optical tweezers to basically kick away bacteria. And yeah, again, sort of a little silly and not sort of something I would have thought of, but turns out to work pretty well.
Thank you. Well, Sydney, do we have any questions coming in?
I do not see any questions coming in, but I enjoyed this talk a lot. I thought it was really neat.
Thank you.
Yeah.
Well, maybe we'll give it some time here. Liv, did you have any questions?
Sorry, I think this is my son in the background there. Um,
I do not have any of my own questions, but I am excited to research more about this. And maybe I will after that.
So yeah, one of the things that I love about this stuff is that it gets it involves a lot of the stuff that you talk about in like intro optics and E&M. So it's always fun to for me to it's like yeah this is it's the stuff that we talk about in class really has some real world applications.
Well, that was one thing I was going to mention out there for maybe the younger viewers that are in the audience that might be just starting out their physics courses and stuff. Some of the applications of what they're learning in the class might not specifically, mention the word optical tweezers, but in order to understand the physics, they have to go through the standard courses to be able to understand the applications of these. So it's not like you're going to maybe be specifically talking about optical tweezers in a particular class, but understanding how it works is sort of a culmination of all your undergraduate and then graduate work, and it all builds up to understanding the physics in different applications.
I wish I would have got to talk about optical tweezers. I took optics here and it was like super, yeah, it was like a super baseline level course. And that's how I completed my physics minor was with optics, and hearing like the true application of Snell's law and all that stuff was really neat. So I really like that.
Yep, you got to start somewhere, and it's always usually with the basics. But without doing the basics, you can't get to understanding the more complicated topics, right? So you can't jump ahead. Well, if we don't have any more questions from the chat, keep in mind that you can share this link, and this link will be available on our YouTube channel for the Society of Physics students here. So you can always sort of publicize that and get this talk out there to more people that you would like. But I definitely want to make sure to thank you again for donating your time tonight with us. And I greatly appreciate your talk. It was very nice and very well informative.
Well, thank you all again for having me, and I hope you all have a lovely evening and good luck with the rest of the semester.
Thank you.
you.
Thank you. You too.
All right,
Have a
take care
nice
now.
evening.